All right, so you've got that big plate tectonics test coming up, huh?
Oh, yeah.
Well, good news. You're in the right place. We're going on a deep dive into earthquakes and volcanoes and how those continents got to where they are.
And of course, how those
What?
plates...
Exactly,
Exactly.
actually tectonize.
I like that. Tectonize.
Yeah,
By the end of this, you're going to be a rock star on that test.
absolutely. And, it's amazing what we can learn from the Earth's history
Right.
and how those lessons can help us understand what's happening right now, today.
Totally. We're not just memorizing a bunch of facts here, right? We're going to become Earth detectives.
I like that.
So, to kick things off, let's travel back in time.
Okay.
Way back to when all the continents were just hanging out together in one giant landmass.
Yeah, Pangaea.
Pangaea.
Yeah, supercontinent.
About 300 million years ago?
I mean, think about it.
Yeah.
Antarctica
Right.
and Africa,
Yeah.
just neighbors.
Neighbors.
So it was Alfred Wegener who first came up with this
Yeah.
kind of wild idea of continental drift.
It was a pretty radical idea at the time.
I mean, how did he think of this?
Well, he had some pretty good evidence, matching mountain ranges, rock formations
Okay.
on continents that are separated by, huge oceans.
Right. It's like finding two puzzle pieces that fit perfectly, but they're like miles apart.
Exactly. That's a great way to put it.
And then there's the
Fossil friends.
fossil friends.
Yes.
Identical fossils found on different continents.
Now separated by vast oceans?
Yeah. I mean, how did those penguins end up so far apart?
It's a head scratcher for sure. And while Wegener's theory of continental drift was a brilliant first step,
Right.
it was the development of plate tectonics that really revolutionized our understanding of the Earth.
Okay, so let's break down this plate tectonics thing.
Yeah, let's do it.
What exactly are these plates, and why are they always on the move?
So imagine the Earth's crust not as this solid shell, but broken up into these massive puzzle pieces, these plates.
Right.
And they're always shifting, bumping into each other,
Yeah.
pulling apart, sliding past each other. It's like a big geological dance party down there.
That's a great way to put it. No wonder the Earth isn't perfectly smooth.
Exactly.
But all this movement, that creates the different types of boundaries, right?
It does.
Like those divergent boundaries I've heard about.
Yeah, so at divergent boundaries, the plates are pulling apart. Think about slowly ripping a piece of bread in half.
Okay.
You get that gap forming in the middle.
Yeah.
That's where new crust is formed as magma rises from the mantle.
So those mid-ocean ridges where the new crust is being born, those are divergent boundaries.
That's right. And then we have convergent boundaries where the plates collide head on.
I have a feeling things get a little more dramatic at convergent boundaries.
You could say that. When two continental plates collide, they buckle and fold,
Okay.
pushing up those incredible mountain ranges like the Himalayas.
Wow.
But when an oceanic plate collides with a continental plate,
Uh-huh.
the denser oceanic plate dives under the continental plate.
Okay.
And that creates what's called a subduction zone.
So all that pushing and shoving, that leads to some pretty intense earthquakes and volcanic eruptions, right?
Absolutely. Convergent boundaries are hotspots for that kind of geological activity.
Right.
And speaking of hotspots, we can't forget about transform boundaries. This is where plates slide past each other horizontally.
Oh, so like the San Andreas Fault?
Yeah, great example.
That's a pretty slippery situation.
It is. And the friction from that sliding can trigger some powerful earthquakes, which is why the San Andreas Fault is so famous.
Okay, so let me get this straight. We've got our three types of plate boundaries.
Mm-hmm.
Divergent, they're pulling apart. Convergent, they're crashing together. And transform, they're sliding past each other.
Exactly. You got it.
But how do earthquakes actually happen? Is it just all that plate movement that causes the ground to shake?
It's a little more complicated than that. All that movement builds up stress in the rocks along those plate boundaries. Eventually, the stress gets so high that it exceeds the strength of the rocks, and they fracture,
Oh, wow.
releasing a burst of energy in the form of seismic waves.
Potent.
And those waves travel through the earth, causing the ground to shake.
So it's like bending a stick until it snaps. All that energy has to go somewhere.
Exactly. And we measure that energy release using something called the Richter scale.
Oh, yeah.
It's a logarithmic scale,
Logarithmic.
which means each whole number increase on the scale represents a 10-fold increase in the amplitude of those seismic waves.
So a magnitude 7 earthquake isn't just a little stronger than a 6, it's actually 10 times stronger.
That's right. And the energy released increases even more dramatically. A magnitude 7 earthquake releases about 32 times more energy than a magnitude 6.
Wow, that's crazy. So that's why even a small jump on the Richter scale can make a huge difference in the destruction, right?
Exactly.
Now, what about those seismographs I've heard about? Those are the instruments that measure all of this, right?
Yes. Seismographs are these incredibly sensitive instruments that detect and record those seismic waves. They have a weighted pen that stays still
Okay.
while a rotating drum of paper vibrates with the ground motion.
Right.
And this creates a visual record of the earthquake called a seismogram.
So these seismograms, can they tell us, like, how far away an earthquake was, how strong it was?
Absolutely. And they also tell us about the different types of seismic waves, like P waves. Those are the fastest. They arrive first.
Okay.
They're compressional waves, kind of like sound waves traveling through air.
Like a push and pull motion.
Exactly. Then you've got the S waves. They're slower,
Right.
and they travel in more of a side-to-side motion,
Okay.
kind of like ripples in water. And then last but not least,
Yeah.
the surface waves. They're the slowest,
Okay.
but often cause the most damage. They travel along the Earth's surface, making the ground roll and sway.
So the P waves are the speedsters, S waves shake things up a bit more, and the surface waves are the real troublemakers.
That's a great way to remember it.
All right, got it. Okay, let's switch gears and talk about volcanoes.
Okay, yeah.
They're so fascinating, even though they can be a little terrifying.
Well, they are a powerful reminder of what's going on beneath our feet. Most volcanoes form at convergent or divergent plate boundaries,
But-
where magma, that molten rock from deep within the earth, rises to the surface.
So convergent boundaries where plates are colliding and divergent boundaries where they're pulling apart, those are like volcano hotspots.
Exactly. But volcanoes can also form in the middle of a plate over what we call hot spots.
Wait, hotspots, what are those like little blowtorches under the Earth's crust?
That's a great analogy. A hotspot is basically a plume of unusually hot magma rising from deep within the mantle, and this magma punches through the crust, creating volcanoes.
Wow.
And as the plate moves over the stationary hotspot, it can create a chain of volcanic islands like the Hawaiian Islands.
Oh, so Hawaii is basically riding a hotspot wave.
Exactly.
That's pretty cool.
Yeah.
But not all volcanoes are created equal, right?
Right.
We've got our regular volcanoes, and then there are supervolcanoes.
Ah, yes, the sleeping giants. Supervolcanoes are capable of eruptions that are thousands of times larger than anything we've seen in recorded history.
Okay, supervolcanoes definitely sound like something to keep an eye on.
They do.
But before we, get into those, let's shift gears for a second, talk about something a little less explosive. The law of superposition.
Oh, the principle that helps us unravel Earth's history.
Exactly.
Think of it like a stack of pancakes. The oldest pancake is at the bottom, right?
Okay, I like where this is going.
It's the same with rock layers.
So the oldest rocks are usually at the bottom, with younger rocks layered on top.
Exactly. This simple principle allows geologists to piece together what happened in Earth's history.
So if we find a dinosaur fossil in a layer of rock, below a layer, with, say, early mammal fossils, we know the dinosaurs came first.
Precisely. The law of superposition is like a geological time machine,
Yeah.
It allows us to look back in time and understand the sequence of events that shaped our planet.
This is all super fascinating, but I bet our listener, who's prepping for that test, might be wondering how this all ties back to plate tectonics.
Yeah, that's a great point. Understanding the law of superposition is essential for studying plate tectonics.
Okay.
It helps us figure out the age of rocks formed at different plate boundaries, track the movement of continents over time,
Right.
and even reconstruct ancient environments.
So by looking at these layers of rock, we can actually see evidence of past earthquakes, volcanic eruptions, even the shifting of continents.
Exactly. It's like piecing together a giant puzzle,
Oh, cool.
using the rocks and fossils as our clues. And speaking of puzzles, remember those matching mountain ranges and fossil friends we talked about earlier?
The evidence that Wegener used to support his theory of continental drift.
Exactly. That evidence, combined with our understanding of the law of superposition and plate tectonics, paints a pretty remarkable picture of Earth's dynamic history.
Wow. I'm starting to feel like a real Earth detective now. So we've covered a lot of ground in this first part of our deep dive.
We have.
From Pangaea and continental drift to the different types of plate boundaries, the mechanics behind earthquakes,
Right.
and how volcanoes form.
And we even touched on the law of superposition, how it helps us unlock the mysteries of Earth's past.
We've got a lot more to explore, so make sure to stick around for the next part of our deep dive. We're going to keep going deeper into this fascinating world of plate tectonics.
Yeah, it's going to be good. So welcome back to our deep dive into plate tectonics.
We've been talking about all this action happening under our feet.
Right.
The shifting plates, the rumbling earthquakes, those fiery volcanoes.
It's pretty incredible to think about.
It is.
These processes have been shaping our planet for literally billions of years.
I know, and speaking of shaping the planet, we were talking about supervolcanoes earlier.
Yeah.
They sound pretty intense. What exactly makes them so different from, like, regular volcanoes?
Well, it all comes down to the magnitude of their eruptions.
Okay.
Supervolcanoes, they release a massive amount of material, at least 1,000 cubic kilometers.
Oh, that's a lot.
Which is enough to blanket like whole continents in ash.
Oh.
And potentially even trigger like global climate change.
1,000 cubic kilometers? That's hard to even picture.
Yeah, it's a lot.
So how does that compare to a regular volcanic eruption?
Okay, well, think about the eruption of Mount St. Helens back in 1980.
Oh, yeah?
That was a significant volcanic event.
For sure.
But it only released about 1 cubic kilometer of material.
Okay, so supervolcanoes are like on a whole other level.
Totally different scale.
But thankfully, they don't erupt very often.
No, super eruptions are incredibly rare. They happen on average every 100,000 years or so.
Okay, that's reassuring. But I'm still curious. Are there like any warning signs that a supervolcano might be about to erupt?
Well, scientists are constantly monitoring the known supervolcano sites for any signs of unrest. Things like ground deformation, changes in gas emissions, or increased seismic activity.
So it's not like they just blow their top out of nowhere.
No, there's usually a buildup, a series of, escalating events before a major eruption.
Okay.
Predicting the exact timing is really difficult.
Yeah, of course.
But this monitoring, it helps us understand the risks and maybe even gives us some early warning.
That's good. Now, we talked about how earthquakes are measured on the Richter scale.
Right.
But what makes some earthquakes so much more destructive than others?
There are several factors at play. The magnitude, obviously, is a big one.
Yeah.
The higher the magnitude, the more energy is released, the more potential there is for damage.
Right.
But depth is also important.
Okay.
Earthquakes that occur closer to the surface, they tend to cause more shaking.
Oh, so a magnitude 6 earthquake that's shallow, that could cause more damage than like a deeper magnitude 7 earthquake.
It's possible, yeah. And then the type of ground that the seismic waves are traveling through, that also matters.
Oh, no.
Loose, unconsolidated soils, they can amplify shaking, while solid bedrock, it tends to dampen it.
That makes sense. It's like shaking a bowl of jelly versus a block of wood.
Exactly. And then, of course, there's the proximity to populated areas.
Right.
An earthquake in a remote area, it might barely register, while a smaller earthquake near a city, that can be devastating.
Right. So it's kind of a combination of factors.
It is.
That determines how much damage an earthquake causes.
Yeah, absolutely. So we've been talking about these destructive forces of plate tectonics, but we can't forget about the constructive forces, too. Think about mountains, for example.
Oh, yeah, those majestic peaks. How do those form?
We talked about one way earlier with convergent plate boundaries. When those two continental plates collide, they buckle and fold, pushing up those impressive mountain ranges like the Himalayas.
Mount Everest is basically the result of two massive pieces of Earth smashing into each other.
Yeah, pretty much. But mountains can also form at divergent boundaries.
Oh, really?
Remember those mid-ocean ridges where new crust is being formed? Well, sometimes those ridges rise above sea level and they form volcanic mountains.
Wow. I never knew mountains could form in so many ways. It really shows just how powerful these tectonic plates are.
It's incredible, right? And just like with earthquakes, the formation of mountains, it's a slow and powerful process. It plays out over millions of years.
You mentioned earlier that plate tectonics has been shaping our planet for billions of years. What might our world look like, say, millions of years from now?
That's a fascinating question. Scientists believe that Pangaea, it wasn't the first supercontinent.
Oh.
And it definitely won't be the last.
So you're saying the continents might all come together again someday?
It's possible. The continents are constantly in motion. It's driven by those powerful convection currents deep within the Earth's mantle.
So it's like a slow-motion dance, with the continents as the partners constantly shifting positions over millions of years.
Exactly. A dance that's been going on for billions of years, and it'll continue to shape our planet for billions more.
That's pretty mind-blowing. It makes you realize that even something as seemingly solid as the Earth's crust is always changing and evolving.
And it really highlights how everything on our planet is connected.
Right.
From the tallest mountains to the deepest ocean trenches, everything is tied together through this intricate dance of plate tectonics.
This has been such an amazing journey so far. Before we wrap up our deep dive, though, there's one more crucial concept I want to revisit.
Okay.
The law of superposition.
Yeah, that's an important one, especially when we're trying to understand Earth's history.
Right, exactly. So let's remind our listener why this pancake principle is so important.
Okay, so remember, the law of superposition states that the oldest rocks are usually at the bottom of a sequence, with younger rocks layered on top.
Like a timeline etched in stone.
Exactly. And this principle allows geologists to determine the relative ages of rocks and fossils, which is crucial for reconstructing the history of plate movements.
For example, if we find, say, marine fossils in a layer of rock that's high up in the mountains, we can guess that that area was once underwater.
That's right. It suggests that tectonic forces uplifted the seabed over millions of years.
So the law of superposition kind of helps us connect the dots between different pieces of evidence.
Yeah.
Like those fossil friends Weeders found on different continents.
Absolutely. By combining our understanding of plate tectonics, the law of superposition, and other geological principles, we can build a comprehensive picture of Earth's dynamic past.
Yeah.
And even make some predictions about its future.
This has been an incredible deep dive. We've covered so much ground today, from the basics of plate tectonics to the awesome power of supervolcanoes and the super important law of superposition.
And throughout it all, we've seen how these processes have shaped our planet for billions of years and continue to shape it today.
So we're going to take a quick break, but make sure to come back for the final part of our deep dive.
Yeah, we're going to wrap things up and leave you with some final thoughts to consider as you continue to explore this amazing world of plate tectonics.
Welcome back. So we've been on quite a journey through the world of plate tectonics.
We have. From those massive plates always moving to those powerful earthquakes and volcanoes.
I mean, it's pretty crazy to think about something as solid as the Earth's crust constantly changing.
It is. And remember, all this movement, it's powered by those convection currents deep inside the Earth. It's like this giant engine that's always churning and driving the plates across the surface.
You know, before the break, we were talking about that law of superposition, how it's like a window into Earth's history.
Yeah.
We can see evidence of ancient earthquakes, volcanic eruptions, even continents moving, all from looking at those layers of rock.
It's really a fundamental principle, you know? It helps us understand the relative ages of rocks and fossils, gives us this framework for figuring out Earth's past.
And we were talking about the continents, maybe all coming back together someday, forming a new supercontinent.
It's true. If you look back at Earth's history, supercontinents have formed and broken apart over and over again. It's a cycle, billions of years in the making, all thanks to those moving tectonic plates.
So the Earth's always changing, even on a time scale that's hard to even wrap our heads around.
Exactly. And all these changes, they have a huge impact on life too, right? The way continents move affects ocean currents, climate patterns, where plants and animals live. It's all connected.
So as we wrap up our deep dive today, what's one key thing you want our listeners to remember, especially with that big plate tectonics test coming up?
You know, I think the most important takeaway is that plate tectonics is like a unifying theory in geology. It explains so much about our planet: mountains, volcanoes, earthquakes, even where we find fossils. It helps us see the Earth as this dynamic, always changing system.
That's such a good point. It's not just about memorizing facts for the test. It's about understanding those fundamental processes that have shaped our planet and still are shaping it today.
Absolutely. It's a reminder that even the things that seem super solid on Earth are always in motion, always changing.
Well said. We've covered so much in this deep dive. Hopefully our listeners feeling more ready for that plate tectonics test.
And remember, the key to learning anything is to stay curious, keep asking questions, make connections. That's how you really understand something.
Absolutely. So to everyone listening, keep exploring, keep learning, and never lose that curiosity about the world. And when it comes to plate tectonics, the Earth's always full of surprises.